Welcome to Phenomenon Radio, the show that covers thought-provoking breakthroughs in the fields of UAP UFOs to discover fascinating truths, first-hand accounts, and investigative insights into the expanding confluence of physical and mental exposure to this worldwide phenomenon. Hosted by Emmy award-winning investigative journalists, Earthfiles reporter and editor Linda Moulton Howe, and world-renowned experiencer of the 1980 Rendlesham Bentwaters incident, John Burroughs. And now, leading off tonight's program, here's Linda Moulton Howe.
Almost a year ago, on September 9th, 2017, there were headlines around the world: Earth's first known interstellar visitor. The excitement was about a strange, long, and flat object that was discovered by researchers using the Panoramic Survey Telescope and rapid response system known as PAN-STARRS on the island of Maui. It was dubbed Oumuamua. That's a Hawaiian word that means scout or leader in a battle. Astronomers could tell that the 1,300-foot long, which is 400 meters, Oumuamua was not from our solar system or the Kuiper Belt or the Oort cloud based on its hyperbolic orbit. That showed that the object was not gravitationally bound to our sun, and it was not a comet. There was no long tail, no cloud-like coma around its core, even after getting relatively close to our sun. So it was soon classified as an asteroid that had traveled from someplace else in this universe. And then, 8 months later, the May 21st, 2018 monthly notices letters of the Royal Astronomical Society published a research paper by French and Brazilian scientists that investigated another strange asteroid called 2015 BZ509. It was discovered 3 years ago doing something very odd. It was orbiting the sun clockwise, unlike all the other planets and most asteroids in our solar system, which orbit around our sun counterclockwise. The clockwise asteroid also moves in Jupiter's orbit. With computer modeling going back in time to near the beginning of our solar system, the scientists showed that asteroid 2015 BZ509 has been in its current orbital state since the formation of our solar system. That means it was captured from the interstellar medium 4.5 billion years in the past. Because when Earth and the other planets were forming, BZ509 already had a primordial large inclination orbit that computer solar system models today cannot render. All of this and more is of great interest to Professor Avi Loeb at Harvard University, who is chairman of Harvard's astronomy department. He is also chairman of the Breakthrough Starshot Advisory Committee. Starshot was first funded with $100 million on April 12, 2016, by Russian venture capitalist and physicist Yuri Milner. Their goal is to use a very powerful beam of radiation from lasers that you focus on a sail carrying a compact computer, camera, and navigational device that can be pushed by the light, starting at 20% of the speed of light. Avi Loeb told me in an interview, quote, "Then you launch that small payload, the Starshot, in the direction of the nearest star, such as Alpha Centauri, 4 light years from Earth. And when the Starshot gets to that nearest star, then it would send photographs of whatever planet in that system might have life. And that would be an image coming back to Earth," close quote. Another scientist who shares Avi Loeb's excitement about interstellar technologies and Starshot is Richard K. Obousy, PhD physicist and director for Icarus Interstellar, a nonprofit research foundation dedicated to researching technologies that will enable breakthroughs in interstellar travel. Dr. Obousy is also a regular guest contributor for Discovery Space News. When he earned his PhD in theoretical physics in 2008 from Baylor University in Waco, Texas, his dissertation focused on compactified dimensions and understanding the nature of the zero-point vacuum in quantum field theory. Prior to studying for his PhD, Dr. Obousy worked for the UK Defence Evaluation and Research Agency as a radar physicist. Recently, he contributed a chapter for a book entitled Going Interstellar, edited by managers at NASA's George Marshall Space Flight Center in Huntsville, Alabama. After this short break, Dr. Obousy joins Phenomenon Radio to talk with us about why humans on Earth should be trying to go interstellar when we haven't yet been to Mars and the other bodies in our solar system.
You're listening to Phenomenon Radio live exclusively on KGRA-DB, the Global Radio Alliance. Don't go anywhere, folks. John Burroughs, Emmy Award-winning investigative journalist Linda Moulton Howe, and tonight's very special guest, Dr. Richard Obousy, will join the show right after these messages. Stay with us. Thanks for joining us tonight, everybody, on Phenomenon Radio Live, again, exclusively right here at home on KGRAradio.com. All right, it's time for the interview we've all been waiting for all week with our very special and honored guest, Dr. Richard Obousy. To start tonight's interview, here's Linda Moulton Howe. Linda?
Thanks, Race. And Dr. Richard Obousy, welcome to Phenomenon Radio.
Thank you very much. It's an absolute pleasure to be speaking to you and to be speaking to all your listeners today.
Thank you. And let's pick up where I raised this question as we went into the break. Why should humans on Earth be trying to go interstellar when we haven't yet been to Mars and other bodies in our own solar system?
I think that's a fantastic question. And, before answering directly why we should go, let's sort of motivate this a little bit and say, well, what is interstellar travel? So interstellar travel involves sending robotic crew or even crewed spacecraft to other solar systems. So let's talk about where we're at today. So we've launched satellites into Earth orbit, the first being 4th of October 1957 with Sputnik. We've launched human beings into Earth orbit. We've landed human beings on the moon. We've sent our robotic probes to all the planets of the solar system, but we've never been to the stars. So let's talk about some of the reasons we might want to go to the stars. Well, first off, there are some scientific reasons. So en route, there's the study of the interstellar medium. So this would be from purely scientific purposes. We don't really know much about the interstellar medium. That is the space that separates, the vast space that separates stars. Once we get there, we can perform more detailed astrophysical studies of the target star. And then, of course, what's really exciting are the planetary studies. So we have discovered many, many exoplanets, some of the most famous being from the NASA Kepler space telescope. So we believe that we know that there are planets orbiting other stars. We know a fraction of those planets are Earth-like in the sense that they have roughly the same Earth gravity. They're roughly the same size. They may have liquid water on them. They're in what's called the habitable zone, which is a distance from the host star that's neither too far nor too close, so that you can have liquid water. So I think that's a very exciting prospect. And then, even more tantalizing, if there are Earth-like planets out there in the habitable zones that have liquid water, is there any life on those planets? What would that life be like? Would it be primitive, organic life? Would it be carbon-based? Would it be life like ours? And then going a step further, could intelligence have evolved on other planets? So I think there are lots of very exciting reasons. And then, so they're really the scientific reasons. But let's talk about some other motivations as well. One is the longevity of the human race. So, right now we've got all our eggs stacked in one basket with, the entire human race on Earth. Potentially we could expand out into the solar system, and potentially, people are talking about the idea of terraforming over a period of many centuries, other planets. So Mars is one example. There's a very famous trilogy called the Mars Trilogy. It's a science fiction book, but written by a NASA scientist who had, really done his research and sort of explored the possibility of converting Mars to an Earth-like environment. But at some point the sun is the sun's going to go red giant. I mean, we have to leave at some point, otherwise we're going to go extinct. I mean, that's an absolute mathematical certainty. So the longevity of the human race is another motivation. But I think my favorite one, and it's far more esoteric, is that simply it's an expression of who we are. We're a curious and energetic species. We've always explored. We've always pushed our boundaries, and so in some sense it's part of that human story. But I think it's nobody doubts that it's going to be hard and it's going to be expensive. I mean, we haven't been back to the moon since 1972. There's not a huge motivation to put much of our national budget into space exploration. So it's going to be hard. And to put things in context for your listeners who may not be familiar with just the vastness of the universe and the vast distances between the stars that are in our own galaxy, we actually already have 4 U.S. spacecraft which are traveling in interstellar space. That wasn't their mission. That's a byproduct of their mission within our own solar system. So they're the Voyager and the Pioneer probes. And as an example, Voyager 1 is traveling at 17 kilometers a second, which is 38,000 miles an hour. Now, one of our closest neighbors, Proxima Centauri, is a little over 4.2 light years from Earth. And the Voyager probe, traveling at that great rate that it is traveling at, would take around 75,000 years to reach just the closest star. So that just really brings into focus just how profoundly challenging interstellar travel is. I mean, we can get into Earth orbit. It's about 100 miles, give or take a little bit. Low Earth orbit is about 100 miles. We can get there in a couple of minutes with our rockets. We can get to the moon in just a couple or 3 days. Mars, several months, close to a year, about 9-10 months. But then to get to the stars, we're talking, like I said, it's not feasible in timescales of a human lifetime.
Well, let me add something in here, inserting from Avi Loeb on Starshot. We were talking about that light takes on average 3 minutes and 20 seconds between Earth and Mars. So a one-way, quote unquote, telephone call from here, or light call, would be 3 minutes and 20 seconds. And he said, we're going to try to get Starshot going, addressing your whole issue of 75,000 years to get to 4 light years. He said, if we can start with testing sometime soon at 20% the speed of light, and then keep moving up toward getting closer and closer to the speed of light, that we could start launching toward Alpha Centauri, and that each year we might make a launch, and pretty soon we might have something that is going to bypass all of the early launches and be as fast as nearly 4 years to get there. Do you think that's true?
Yeah, I mean, I think that's there's plenty of really good talking points there. So, there's this first idea that you hit on towards the end of over a period of decades and centuries, our space probe are going to get progressively faster. So, let's say the example of we launch a Starship 50 years from now, traveling at 1% the speed of light. It's going to take hundreds of years to get to the closest star, but then in 200 years we discover warp drive and faster than light propulsion, and the probe that we launch centuries later ends up getting there faster. But I don't think that's a good excuse. I mean, we can't predict the future. If we have the technology today, let's go ahead and exploit that technology, utilize and harness that technology, because we can't rely on the fact that one day we'll travel faster than light or we'll travel at the speed of light. And the other talking point there, I think, is there's some really exciting things going on, obviously, with Starshot, but it's a new paradigm in propulsion, in the sense that what we currently use for getting objects into space and traveling throughout the solar system is chemical rocket fuel. And using that for interstellar travel is it's not a realistic possibility. So, we talked about the 75,000 years with the Voyager probe, which were launched using chemical rockets. And the challenge becomes more apparent if you consider one of the most basic equations that govern spaceflight, and that's the Tsiolkovsky rocket equation. And what it does is it tells you how much propellant you need for a given rocket mass and fuel type. And if you plug the numbers into the Tsiolkovsky rocket equation using chemical propellant to get to Alpha Centauri in timescales of a human lifetime, basically you'd need to go at 10% the speed of light. You'd actually need more rocket fuel than there exists mass in the known universe.
Really?
So, yes. Now, the problem can be mitigated using multi-staging, but it still gives some sense of the absolute, scale of the problem. You can't use chemical rockets to get to an appreciable fraction of the speed of light. I mean, it's just it's an impossibility.
But you can use light to push toward the speed of light. And that, to me, in the animation I've seen and talking with Avi Loeb, where the idea that whether we end up starting with one laser or 5 or 7, and if we get them on the moon, we won't have the atmosphere to contend with, and that if we get a laser launch on the moon, we might be able to reach accelerations faster, and that at least having the Starshot getting to Mars quickly, if Elon Musk gets there in 2020, which he insists he's going, we're going to start having television programs and some kind of communication system between the Earth and Mars, and Starshot could become like the Pony Express, of distant times.
Yeah. And, I mean, there's some great points. For those who maybe think it's too fantastical, I think it's interesting to think about where we've come from, in the last century or so. And I think we tend to overestimate what we can do on short timescales. I do this all the time. I start a project. I think it will take a few weeks. It takes much longer. But I think we tend to dramatically underestimate what we can accomplish on longer timescales of decades. So I remember I grew up on science fiction. I used to watch Star Trek: The Next Generation in my teens, and they used to have the Starship Enterprise, and they had these pads, these kind of portable computers that they would walk around and they would type stuff in. And I remember in the 1990s just thinking to myself, wow, that really is 24th century technology. And then 15 years later, we're all walking around with these iPads, with these portable devices. And another example is, we can't forget the Kitty Hawk, this flimsy contraction, the first control-powered and sustained heavier than air human flight. I mean, that flew in 1903. And then in 1958, we saw the debut of transatlantic jet-powered passenger aircraft. So, 55 years later, we went from this wooden, flimsy contraction to essentially transatlantic jets. So, another example I think is quite interesting. There are different types of, we can talk more about this during the call, but there are many different alternatives to chemical rockets. And so breakthroughs in physics can very quickly lead to breakthroughs in technology and specifically space travel. So here's an example. Let's talk about the atomic structure of matter. So the experimental verification of the electron, that was in 1897 by J.J. Thomson, and then 20 years later, Rutherford discovered the proton, and then in 1932 we had experimental verification of the neutron. Then, just 27 years after we'd finally figured out the substructure of matter, we had Project Kiwi, which was a project in the United States for nuclear rockets. We built and tested on Earth the first nuclear rockets, just less than 30 years after the actual verification of the atomic structure of matter. So, I think, where will we be in 100 years? Like I said, we underestimate what we can do on timescales of decades and centuries. Will we be building starships before the end of this century?
And isn't there a lot of talk about a whole new propulsion system that might involve controlling the electromagnetic spectrum, and that there are some science papers having to do with zero-point energy, which I hope you will talk about, where if we were accessing energy from the vacuum and we were able to, let's say, move point to point because we figure out how to control gravity and the magnetic field, we would no longer even have to think in Euclidean geometry of thousands of years because we could move point to point in the universe.
Yeah, so I think let's examine. Let's take a step back and say, okay, what is the physics that we do know and the technology that we do know versus the more speculative, like the ones that you've talked about, which actually composed a chapter in my own PhD dissertation and something that I'm very, very excited by. But let's look at some alternatives that we know how to do now that could get us to the stars much more quickly. So I talked about the infeasibility of using chemical fuel for rockets, but you outlined one alternative, that is beamed energy. So that's the propulsion paradigm being explored by the Starshot initiative. Right. And so beamed energy involves using a lightweight cell-like structure, and what you do is you harness the momentum transferred from photons. So we've known since the time of quantum mechanics that photons, light particle, there's this wave particle duality between light. Under certain experiments, light behaves like a wave. Under certain other experiments, light behaves like a particle. And it's very difficult. We can describe it mathematically. We don't really understand exactly why we have this duality. But photons impart momentum. They push against things that they hit. Now, of course, that momentum is very, very, very small. But if you have very high-powered electromagnetic field, like from a laser or a microwave, hitting some very, very light cell-like structure, then you can accelerate that cell-like structure. So beamed energy, you could roughly reach about 20% the speed of light. Now, a disadvantage there is that it's very low payload. So beamed energy is highly unlikely to be used to send robotic explorers or space probes. So, we can talk in a little bit more detail on Starshot shortly, but the probes are very, very tiny. We're talking, right, a couple of centimeters by a couple of centimeters. I mean, they're minuscule. So beamed energy, you kind of, had the phrase of the Starshot being like the Pony Express, but right. I don't think they'll be the workhorse. The beamed energy will be the workhorse of the solar system. They may be these little microscopic explorers, very, very, very low payload ships. But some alternatives. There are. So we've got beamed energy. That's one alternative to chemical rockets. Then there are two forms of nuclear energy. So there's nuclear fission and nuclear fusion. So we have harnessed nuclear fission. We've understood fission for quite a long time now. We had fission bombs from the Manhattan Project last century. And then we figured out how to harness nuclear fission for constructive purposes. We have nuclear power stations now. And I touched on the NERVA project, the Nuclear Energy for Rocket Vehicle Applications, was a project a program done by the United States, and the Russians also had an extensive nuclear fission rocket program. But we've built fission rockets We know how to build them. We haven't flown them in space yet, but we know how to build them. And under certain models, efficient. So there are three different types. There's a solid core, a liquid core, and a gas core. And then there is a variant that's being worked on by a colleague of mine in College Station. He calls it the fission fragment rocket. And we think that could reach up to 1% the speed of light. And so that would be getting to the closest star in a few hundred years. 500 years roughly.
And fission fragment, what exactly? Fission is splitting the atom. Fusion is a concentration like on the sun. And the fission fragment, what is the fragment?
I couldn't go into too much details on the fission fragment rocket. It's been a long time since I looked at it. But essentially, you hit the nail on the head. You have a high atomic mass particle like a plutonium or uranium, and you bombard it with neutrons, and that splits the atom apart. And in doing so, through Einstein's E equals mc squared, liberates energy. Mm-hmm. So and then you mentioned fusion, which is something else that we have good understanding of. So with fusion, we built the first fusion bombs. That's what we call a thermonuclear hydrogen bomb. So we've harnessed fusion for destructive purposes. We're trying to harness fusion for power stations. So we've got the ITER project, which has been going on for decades now, the International Thermonuclear Experimental Reactor, and then you've got a project over here called NIF, the National Ignition Facility, and they each have different ways of fusing matter. But as you mentioned earlier, you get typically you get a low mass atom like hydrogen. You get two hydrogens, you smash them together, and you form a heavier element. You go from hydrogen to helium, and energy is liberated in the process. And actually, that's how all matter. Every single element around today was forged through some nuclear fusion process. Typically, the higher mass elements were forged during supernova explosions, but the lighter elements are easier to do. So
Dr.
Yes.
Ask here, why is it? I remember back in 1978 that Brookhaven was working on nuclear fusion, and then there was a congressional closing down of budgets for working on fusion. Yeah. Why is it that there has been so many push-pull and delays? And what is the biggest physics problem of, I know Brookhaven thought that they were close in 1978, and it's now 2018.
Yeah.
Why do we not see rapid progress on fusion, which would be cleaner and better?
I think that, again, a tremendous question. So going to the first part of your question, why do we get this push-pull? I think there's a lot of politics involved that I couldn't speak to, but ultimately it's going to come down to cost effectiveness. I mean, we talk about the holy grail of clean, renewable energy, but if it's costing tens or hundreds of billions of dollars to get there, when you already have working fission power stations, when we have lots of coal and oil that's been unutilized, yes, it's not popular, it's dirty, but the bottom line is, it's a lot cheaper to mine and harness fuels that we know how to harness than to spend tens of billions of dollars on things that we don't know how to do. So, in a perfect world, we would have the resources and we would put the funds into doing it. But that's not the world that we live in. I mean, I'd have to check the numbers, but we're only spending a few $1 billion a year on fusion research. And if you compare that with, say, the Apollo program, which got human beings, which got us to the moon, converted into, for inflation, the figure is about $150 billion it costs for the Apollo project. So I think when you get enough people together, smart people working on problems, I think you can figure it out. But right now, there's limited resources for it for political reasons. And then in terms of and then to answer the second part of your question, what is the problem? And again, I'm not a fusion expert, but I'll convey my understanding that like I said, there's about 15 or 20 different ways you can accomplish fusion, that you can essentially get the hydrogen atoms to smash into each other with enough energy, namely to be moving fast enough. You have to heat them up. And the popular one that's been explored for a long time is you confine the hydrogen in these tokamak structures, these magnetic fields. And the reason being is this hydrogen is going, you heat it, and it's going so fast, it's moving so fast that it's so hot that if it touched any of the container walls, it would just burn through them. So you have to confine it in a magnetic field. But if that magnetic field, if just a few hydrogen atoms penetrate the magnetic field, then they hit the side of the tokamak, and the fuel gets completely polluted with other contaminants. I'm sure there are some fusion experts that are be laughing at my butchered explanation, but that's roughly my understanding of a 30-second explanation of the challenges of fusion from from using a tokamak. And then there are things,
Yeah, and why are we then so far from getting access to 0-point energy?
So I think that's a good question. So, I mean, I can keep talking. We were talking about fusion. I was going to try and do things linearly. So from what we can do now to what we might do in the deep future. But we can talk about 0-point energy right now.
Yeah, because that's one of your specialties, and we understand that the landscape for fusion and fission to some degree. And what I would love to hear through you is what are the challenges in getting 0-point energy, and could you start by explaining to a general audience how much energy is hypothesized to be in something like a square foot of space?
Yeah, so let's talk a little bit then about 0-point energy. So one of the most advanced theories in physics that we have today is called quantum field theory, and QFT proposes that every point in space can be modeled as what we call a quantum oscillator. So the next question is, well, what is a quantum oscillator? I mean, it's just really a mathematical object that physicists use to explain, to come up with the theories of particle physics. But the fundamental idea is that these field oscillators, these quantum oscillators, can never be strictly at rest, that they're always, due to something called the Heisenberg uncertainty principle, they're always got this 0-point energy, this kind of little wiggle, and because they're wiggling, they're giving off a whole range of different types of radiation. The most powerful, the strongest, the dominant component of the radiation that they give off is electromagnetic radiation. And some of your listeners may have heard about the quantum vacuum, the virtual particles that come into and out of existence. And so the amount of energy, I don't have the number to hand, but it's absolutely vast. I mean, it's many orders of magnitude than we can than you get from nuclear fusion. So the one thing that comes to mind immediately is a thimbleful of vacuum energy liberated would be able to boil all the oceans of Earth. I mean, I think off the top of my head, it's something like 10 to the 24 joules, but I'd have to go look back in my textbook. But it's prodigious. I mean, it's like the difference between going from fire to a nuclear bomb. Right. Is the difference between going from a nuclear bomb to 0-point energy. But the thing is, we don't know how to liberate it. So that's a prediction from quantum field theory. That it's a prediction that there exists that much energy. Now, one of the most salient manifestation of the reality of the 0-point energy comes through an experiment called the Casimir effect, which was one of the major areas of focus for my dissertation. And so this was first explored by the physicist Hendrik Casimir in 1948. And what he said or showed was that if you put two parallel conducting plates, so just imagine two metallic plates and you put them close to each other, this 0 point energy, if you picture in your mind like these little waves of electromagnetic energy, and those waves can be very, very long, they can be very, very short, they can be anywhere in between. Well, he said that in the interior region of these parallel conducting plates, you can only have standing waves form. They're the only waves that can exist. All other waves get sort of destroyed through this process of destructive superposition. So you have a limited number of frequencies that can exist on the interior region of the vacuum of the plates. However, the exterior region of the plates, the anterior portion of the plates, there's no restriction. So you have this vacuum energy asymmetry between the interior and the exterior of the portion of the plates, and the plates are pushed into each other. And so what's really interesting about this is that there is a force that is manifested on these plates that attracts them, that is not due to any of the four fundamental forces of physics. So it's not it's not an electromagnetic force, it's not a gravitational force, it's not a weak nuclear force, it's not a strong nuclear force, which are the four fundamental forces that are responsible for everything that occurs in the universe, every event, every action. This is a type of a fifth force. It's a force that manifests from an asymmetry in the quantum vacuum. So these plates are actually pushed together by the vacuum. Now,
that is then a demonstration of all of that potential vacuum energy. But what we don't know how to do is to lasso it or to get it. But that the Casimir effect is showing us a demonstration of that energy.
That's right, exactly. So essentially, yeah, you hit the nail on the head there. So essentially, we believe that the quantum oscillators are the fundamental substructure of the universe, that they oscillate. And if you were to extract energy from it, there'd be prodigious amounts of energy. And the way that you measure the existence of the reality of the vacuum energy is through this Casimir effect. And this Casimir effect, I should add, this Casimir effect was predicted by Hendrik Casimir, but it's also been experimentally verified many, many times over the decades, with each successive experiment getting more and more precise in terms of the experimental outcome more closely matches the prediction from Casimir himself. But yeah, you've got it. We don't know how to extract that energy. And Robert Forward, a physicist last century, wrote a paper that demonstrated that fundamentally you could extract energy from the vacuum. But I mean, there's all sorts of problems, and it's been many years since I read his paper. But if memory serves correctly, the idea is: imagine you've got these two plates. Imagine you've got these two plates coming together, and you think of some way of extracting energy from the fact that these plates are coming together. I don't know. There's maybe some springs attached to either side, or some mechanical system that can extract energy from the movement of these plates towards each other. What do you do once these plates collide? You have to pull them out again, probably using as much energy as it took to get out in the first place. So yes, in principle, you can extract energy, but no one knows how to do it in perpetuity with energy that comes out greater than break even.
Well, did you co-found Icarus Interstellar with a very specific goal related to the Casimir effect or the vacuum?
Yeah, that's a great question. So the direct answer there is no, but I would like to give you a little bit of background behind Icarus Interstellar, because it's important that we talk about it. And it started. So I've been interested in space exploration and space travel for a long time. I published my first paper on faster than light travel in 2005. And then I got my first peer-reviewed publications on faster than light travel around, I think it was about 2007, 2008. So I have peer-reviewed publications on the topic, and I explored my own model of how you could do FTL. And then in 2009, I was co-founder. I was invited by a British chap who was at the British Interplanetary Society to co-found a project called Project Daedalus. So Project Icarus is the name. So Project Icarus was the successor to Project Daedalus. So let me talk about this, because it all sort of wraps in. So Project Daedalus was a 5-year, the most detailed engineering study of a fusion starship. So it was a 5-year study initiated in 1973 by the British Interplanetary Society, and it was modeled around the rocket was an internal-external hybrid of fusion pulse propulsion engine, and its target was Barnard's star, and its fuel was deuterium helium-3. Its top speed was 12% the speed of light, so you'd get to the closest star on timescales of a human lifetime. And they did this series of about 25 papers, each exploring different facets of the Starship design, the propulsion, the secondary propulsion, the engineering, the fuel. And so this is an absolutely wonderful study. So we launched Project Icarus, so Icarus, son of Daedalus, in 2009. And we built an international team of researchers, and we did all sorts of trade studies, and we peer-reviewed papers, and we started going to conferences. And then, because we were self-funded, and so we put up a website, and we talked about what we were doing, and we used that to get people to recruit people. And then we decided to start taking donations. So we started taking PayPal donations, and we realized that we needed to formalize the organization and create a non-profit business entity. And so we founded Icarus Interstellar. So the name was just taken because the first project we got started was Project Icarus, which was a successor study to Project Daedalus. So Project Icarus was specifically a fusion starship design study. However, the organization we founded, whose name was inspired by that project, was Icarus Interstellar. So we were granted 501c3 status. Co-founders were myself, Dr. Andrea Ciolos, Kelvin Long, Adam Crowell, and Pat Gallia. So the mission statement was to realize interstellar flight before the year 2100. And we said that we would accomplish the objective by researching the science and the technologies that would make interstellar flight a reality. And so we actually broadened our scope from simply starship design studies to being much broader. So we launched a number of other interstellar research initiatives. So we had a project looking at beamed energy propulsion, the type we talked about briefly earlier. World ships, which would be ships that would be moved very, very slowly, but have big populations on them that would many generations later reach their target star. We had antimatter, we had fission rocket, and we even had I headed up the exotic propulsion group actually, and we were looking at things like faster than light travel, wormholes, liberating energy from the vacuum, but as well as research. I mean, this was really a fully functioning organization. We had teams for public outreach, fundraising. We did student recruitment, and we began examining the possibility for an interstellar institute, which would be a physical hub for activities. And then we got a lot of accomplishments. We have the organization is still going. We have about 40 peer-reviewed papers, hundreds of internal trade studies, lots of appearances at conferences. We were involved actually in the winning team of a Pentagon / NASA sponsored contract called the 100-Year Starship. So that was in collaboration with two other organizations. We were sub on the contract. The prime was Mae Jemison, and we tried to work with her and her team for over a year, but she didn't honor the contract that we initially had negotiated. So ourselves and the other organization who teamed with Mae Jemison's organization also departed because she didn't honor the initial agreement we had with us. So that was obviously very disappointing for the organization because this was the first essentially government-sponsored grant for interstellar travel. And
where was the 100-year Starship's target?
The 100-Year Starship was an initiative to kind of kickstart. It was just $500,000, and in the bigger scheme of how much space travel will cost. So it was to kickstart the creation of an organization that could last 100 years and shepherd us, America, human race, or however we want to phrase things, whatever we wanted to do, but shepherd us to becoming an interstellar civilization. So it was an organization created, or supposed to be created, to shepherd us towards becoming an interstellar civilization. But we walked away from that in 2013, and we refocused, and myself and a number of other team who we all collaborated to put on this very, very big conference in Dallas called Starship Congress. So that was in 2013. And there was close to 200 attendees from all over the world. We had Nobel Prize nominees there. We had a lot of the big names in interstellar travel all convened for a 3.5-day conference. And we have run that every 2 years since. So we had 2013, 15, and 17. In 17, we were very proud. We got Miguel Alcubierre, who was the creator of the 1994 warp drive paper that's very, very famous. So he came and gave a talk, and I got to meet him. We had talked by email,
Dr. Obousy, for a general audience, because the Alcubierre concept comes up quite a bit now. Can you explain for a general audience that do not have physics degrees the basic hypothesis of the Alcubierre process?
100% I can. So the basic idea behind getting between 2 points, between point A and point B, is you propel an object somehow through space, okay? You go from point A to B. You do it either by walking, you do it by turning your car engine on and traveling, you do it by flying, you do it by flapping your wings. You physically use some form of locomotion to get from point A to point B. What the Alcubierre concept does is actually shrink the space-time in between point A and B. So rather than actually having to use some form of locomotion to get to between point A and point B, you actually shrink the space-time between point A and point B. So
how do you do that?
Yeah, wow, that's kind of the billion-dollar question. But within the confines of so the known laws of physics, can basically be broken down into gravity, which is explained by general relativity, I should say, which is our explanation of how gravity works, and then quantum field theory, which is an explanation of how the electromagnetic and strong and weak nuclear forces work. So general relativity is our theory of gravity, created in 1915 by Einstein, and actually it was created by other physicists before him, had done sort of all the hard work, but he kind of took the credit for it. Like Riemann is an example of one of the guys who created the field equations that Einstein took credit for. But the idea is that space-time is not this nothing, that it's actually a fabric that can bend, that can contort, and that this kind of this bending of space-time is what's responsible for gravity, and that under extreme conditions, space can expand and contract. And we believe that in the very early epoch of the universe, the first fractions of a second, that the universe expanded at many, many times the speed of light in a phase known as cosmic inflation. And even now, the universe is inflating. We've known this since the 1920s, where Sir Edwin Hubble discovered the recession, the redshift in the galaxies that are receding from us. So we even believe now that space is expanding. And so in Alcubierre's paper, his model was to create a localized contraction, expansion of space-time. So behind the spacecraft, space-time would expand, and in front of the spacecraft, space-time would contract. So you can imagine the way you get, if you can picture in your head just 2 points, A and B, you literally shrink the space-time between them. So that was the idea, the basic idea. And what Alcubierre's genius was, he used Einstein's equations to codify. He used general relativity to codify this. I mean, he did all the math. He figured out, what space-time would look like, how much it would have to curve by. So that's what Alcubierre was famous for.
So would it mean that a spacecraft that was operating in an Alcubierre system would be moving like an inchworm, pulling sort of like collapsing space-time, pulsing? It would be more like pulsing travel?
I think an apt analogy is just simply, it's a little bit of an overused analogy, but just riding on a surfboard. You're kind of traveling on this wave of space-time. The way I picture it is, if you imagine, if you imagine a strand of space-time being a little bit like a piece of string, and you just squash that string together. I mean, that's or another way to think about it. Imagine having an elastic band, a rubber band, and you stretch it out as far as it can go. And that's your point A and point B, and that's space-time as it currently stands now. Now just imagine the tension of that, releasing the tension on that elastic band, so it kind of its length decreases,
right.
It gets closer to each other. That's another way you can sort of picture it in your mind. But that would just be a one-dimensional strand in that example. You'd have to expand that out to the whole 3 + one-dimensional space-time. But yeah, that's...
And this fabric aspect of space-time that comes into also a huge question now that is being debated more and more. Why would the universe at 13.8 billion years from its beginning, why would there be what appears to be increasing expansion energy, which is where dark energy gets thrown into the equation to try to explain the expansion? Do you accept that dark energy is real and is responsible for continuing energy into expansion in this universe?
I think it's an interesting way to phrase the question. Do I believe it's real? I think, I have faith in the scientific process. I have faith in the papers that have been published. And to go back for your readers, so the idea here is let's go back a step. So Edwin Hubble in the 1920s, wherever he looked, he noticed that all the galaxies appeared to be receding from us, that they all seemed to be moving away from us. And then we said, okay, this is due to something we called the cosmological constant, which essentially was making space expand. Okay, but we assumed for a very long time that the rate of expansion didn't change. So you imagine a balloon, and imagine just turning on a pump, and it expands just at this constant rate. It's just growing at this constant rate. And then what we discovered, it's been years since I looked at the papers. I think it was Perlmutter et al. With the authors of the paper. But what they discovered, looking at the recession velocities of distant supernova in different galaxies, was that the rate of expansion was increasing. Right. So what does that mean? So in terms of that model where we had the balloon and it was just growing at a constant rate, now imagine you're just over time you're just turning up and turning up and turning up that pump and putting more and more air into that balloon faster and faster, and so this balloon expands at an increasing rate. And so that's what we think is going on now.
But what would the energy source be for that accelerating expansion? And we're up against a break. When we come back, let's pick up with this mystery of dark energy, and why should our universe have some kind of an energy infusion that is causing there to be an increasing rate in expansion? Take it away, Race.
This 45-minute uninterrupted segment of Phenomenon Radio Live has been brought to you all by OnlineVibes.com, your personal connection to mind, body, and spirit, committed to helping you with healing modalities that can manifest a true and healthy change in your life. Visit the website, folks, at OnlineVibes.com. That's OnlineVibez.com. Tonight's very special guest, Dr. Richard Obousy, will rejoin the show for Hour 2 right after these messages. Don't go anywhere. You're listening to the KGRA digital broadcast station, Salt Lake City, Utah. Before we begin Hour 2 of tonight's interview with Dr. Richard Obousy on Phenomenon Radio Live with John Burroughs and Linda Moulton Howe, it's time for the news, and it's brought to us every week by Earthfiles.com. Here's Linda.
Thanks, Race. Since 2002, my news website, Earthfiles.com, has reported hundreds of animal mutilation cases around the world, including large animals such as cattle and horses, and small animals such as cats, rabbits, and foxes. In Argentina and Chile alone, their departments of agriculture known as SENASA and INTA officially reported in June 2005 that the government agencies had received, quote, more than 3,000 unusual entirely bloodless animal deaths in Argentina and Chile just in 3 years since 2002. Large animal mutilations there have come in cycles, and 2018 now has been a time of many precise, bloodless cattle mutilations. I have several of the eerie, bloodless photographs from law enforcement and from veterinarians right now in the Real X-Files section of Earthfiles.com. But here is an overview of what has been happening just in August of 2018. On the 6th, the Argentina website Clarin.com headlined, quote, surprise in Colonia Duran, mystery of 7 pregnant cows mutilated all at once in Santa Fe province. The 7 pregnant cows were found dead, bearing precise cuts of their tongues and genitals, no traces of blood on the animal or on the ground. The cattle rancher said, quote, the veterinarians cannot explain how it was done, close quote. Earthfiles viewer Carlos Atashian, who lives in Rio Grande, Argentina, volunteered to translate recent news articles this month from Argentina's Santa Fe province. Quote, bewilderment, surprise, and mystery. The small town of Colonia Duran in the San Javier department of Santa Fe province does not understand how 7 pregnant cows showed up mutilated with precise cuts and no blood traces in their tongues, jaws, udders, rectum, and vaginal opening. Mr. Noberto Bieri is a cattle producer in the zone and has been financially damaged by this event that he describes as inexplicable. Quote, veterinarians have come to the mutilation site, and no one can tell me how or with what something like this can be done. I mean, there is no scientific explanation. Everything seems to have been cut with a laser, no traces of blood. The missing parts of the animals cannot be found, close quote. Continuing with the translation, there is another item drawing the rancher's attention. The scavenger animals, the predators, do not touch these dead cows, and there are no flies anywhere on the bodies. All of this unleashed the most diverse explanations. Some talk of strange light showing in the area during the night. Some talk about strange lights in the sky that are not stars. Some others state that they have seen a difficult to describe animal known rurally as the chupacabra, but is not known to actually exist in proof. Mr. Bieri said, quote, there is no poisoning, no electric shock found in the analysis of my 7 dead mutilated cows. Even in nearby locations between Las Laureles and San Javier, we have seen similar mutilation incidents. And the thing about the lights in the sky is truly that I have seen them myself, close quote. On August 5th, 2018, another eerie, bloodless mutilation was discovered in Tostado in the province of Santa Fe, west of Colonia Duran, where the 7 pregnant cows had been found. The Tostado mutilation was found on Sunday, August 5th, 2018. The ranch owner says, quote, this is what we found in the field, razor-sharp cuts with no blood. The animals and the birds did not come near. They would not even eat the remains. I have never seen anything like this, close quote. This is Linda Moulton Howe. Please stay tuned to Earthfiles news updates on KGRA Radio and visit every day my science, environment, and Real X-Files news website, Earthfiles.com, for more on breaking stories about our universe, this solar system, and the planet we live on.
And that's the news, and it's brought to us each week right here on Phenomenon Radio Live by Earthfiles.com. Now back to the interview. Here's Linda once again.
Thanks, Race. And Dr. Obousy, before the break, we were talking about the Alcubierre theory or hypothesis. Do you think it is strictly theoretical?
Yeah, I do. I actually had the pleasure of meeting Miguel Alcubierre last year. So he came out with his paper in 1994. I was 17 years old at the time. I discovered he was doing his postdoc at, I think, the University of Mexico. So he would have been in his probably mid to late 30s, something like early 30s. And I actually didn't discover his work until my final year of university. During my master's degree, I did my final thesis on exotic propulsion and discovered the work of Hal Puthoff, which got me interested in vacuum energy. I discovered the work of Robert Forward. I discovered the work of Alcubierre. And we had talked a little bit by email towards, around about the time we formed initially Icarus Interstellar, but I didn't get to meet him until he came to talk at our last Starship Congress, which we held in California last August. And I was thrilled because, as mentioned, I came up with my own model of faster than light propulsion while I was at graduate school doing my doctorate, and had several peer-reviewed publications on it. And I came from a different angle. I didn't use general relativity. I came from quantum field theory, extra dimensions, and a dark energy angle. And one of the key findings of my paper was that you could do faster than light travel. You could travel at the speed of light using the mass energy equivalent of the planet Jupiter. And there was a lot of other calculations, but that was kind of like the one visual takeaway. How much energy you would need. Well, you'd need basically to convert the entire mass of Jupiter into energy through E equals mc squared. So like from matter, antimatter annihilation. But what was interesting about that calculation was that when Alcubierre did his calculation, you would need unfeasibly large amounts of negative energy to create this distortion, asymmetric distortion of space-time. And one calculation suggested you'd need 10 to the 64 kilograms worth of energy through E equals mc squared to transport something at the speed of light. And that's actually more mass, several orders of magnitude more mass than is in the observable universe. So the initial Alcubierre drive, you'd need more mass than was in the observable universe. And then I was able to bring that down to the mass energy equivalence of the planet Jupiter. But I spoke after him. He gave a presentation, and it's always nice. He was very much sort of an inspiration for me. I came across his work.
What was his comments to you about his own theory? Did he keep it in the kind of the box of it's never going to happen, or did he talk with you about how he thought his Alcubierre theory might be translated into some kind of propulsion system? We spoke a lot at the conference. We had dinner 2 or 3 nights in a row. We got to have a good amount of time talking to him, both privately and publicly. He never once pitched his Alcubierre drive as a future possible propulsion system. He never pitched it as a technology that we could exploit. He always kind of conveyed it and articulated it as, I would go as a theoretical tool to investigate general relativity, a curiosity, but, given the vast energy requirements and the fact that we have no idea how to create negative energy, well, we can create it in very minute quantities in between Casimir plates, but we don't know how to create, direct it, collimate it, create it in large quantities. And there are some other very interesting problems with the idea of a warp drive as well. There's something called causal disconnection. And what that means is once you're inside this bubble, you can never send a signal to the exterior portion of the bubble that's traveling faster than the speed of light to actually stop it. So once you start, you can't stop. There are some. So he never
articulated the idea as a technology that he thought it was ever going to happen. It was more from the perspective of it being an interesting theoretical investigation.
Well, did you talk with him about wormholes and portals and the idea that if we understood the universe better, that we might be able to move point to point through areas where magnetic fields collapse and that there might be wormhole travel in the future?
We didn't speak about wormholes, and I don't think there was anyone speaking about wormholes at the conference, and that's it's certainly not my area of expertise, so I couldn't speak with authority on wormholes. But, as you mentioned, that the idea is that you create this hole, if you like, in space-time that connects one region to another distant region, and the idea is that you could travel instantaneously between 2 points in space using a wormhole. But we didn't talk specifically about wormholes. I did talk about my own warp drive theory, though.
Well, I remember being at a lunar, it was a conference that in Houston about 10 years ago, and there was an astronaut who was the keynote speaker, and his entire presentation to the Lunar and Planetary Institute was Earth is an unstable planet, and that we have to be working all of the time trying to get ourselves into a base on the moon, on Mars, and beyond, because if humans remain putting all their eggs in the Earth basket, that eventually there will be existential events based on the 4.5 billion years of Earth turning into a snowball, volcanic, and all of the things that have happened on our planet. And in that context, it was very interesting to hear an astronaut laying out for an extremely large audience of lunar and planetary scientists his reason and NASA's reason for saying we have to get people off of Earth, we have to get bases beyond.
Mm.
I mean, that's what you thought.
Yeah, and I 100% agree with that. I've always been fascinated by space exploration, space travel, and I mentioned it earlier that we have all our eggs in one basket here, and there are multiple reasons to go, but one of them is the protection of humanity, the survival of our civilization. And there have been 7 mass extinctions in the history of Earth. The last one, it was about 50 million years, 60 something million. There's been multiple mass extinctions in the history of Earth, and there's nothing that says that there won't be another mass extinction. And some of the ideas of what have caused these mass extinctions, and that's when 90% or more of life on Earth dies through some cataclysmic event. Popular extinction scenarios are big asteroid impact, supervolcanic eruptions. So there's nothing we could do if there was a huge asteroid headed our way, planet destroying, but extinction level event asteroid. There's really nothing that we could do about it. So I quite agree. From a survival imperative, I think it's important that we do build lunar bases. We could start with bases under the oceans. I mean, that's going to be many orders of magnitude easier, because you're talking about the vacuum of space. It's cold. There's nothing there. You have to, you might be lucky if you get some ice there, but you can start with sea colonies first, because
Do you mean literally on the bottom of the oceans and the seas? That's 2/3 of the world's acreage, so to speak. So if we were able to put human populations where the water is, it would take a big pressure off of the land.
Yeah, exactly. And I think there's this sort of misconception that the Earth is overpopulated. I mean, there's obviously a lot of people here, and we do have to get a handle on the population problem. But that's because most people, I don't know the numbers, but I would imagine in the high 60, 70, 80%, I would imagine most people live in cities. Very few people live in urban areas, like out in the countryside. So, and cities are typically cramped, but cities make up only a tiny fraction of the the surface area of the Earth. Most of the Earth is empty. Most of the Earth is forests and fields and just all this, this land that's not being used. So I think that there are. I mean, look at Alaska, for example. I mean, it's almost the land area of the contiguous United States, and there's less than 1 million people that live there. I think it's about 500,000 people. Look at how vast Canada is, and then there are some of the northern states like Wyoming and Montana. They have very, very low populations. And that's just the United States I'm talking about, and there's lots of other places like that. But as we, in terms of needing to go to space for space, I don't think that's a very good argument. I think there's plenty of space here on Earth, and then, like I said, there's cities underwater, and then there was even this chap wrote a very interesting book called "Colonizing the Galaxy in 8 Easy Steps." His name was Marshall Savage, and he had this 8-point plan for how we could get from now to the stars in 8 steps. And his step 1 was to create these floating cities. And he had this idea about how these cities, they would use ocean currents to extract energy, and they would mine local ocean resources, and they would grow oysters, and that would form part of their economy, and they would sell this algae as food as part of their economy. And he did the calculations on how much it would cost to get one of these floating cities going, and it was a few $100 million and a few hundred settlers. And then he calculated how much revenue it would generate per annum, and it was like $600 million per annum. And he suggested having several of these, and the colonists then using that money to fund the next stage of space exploration, which would be an orbiting space station, and then the next would be a colony on the moon, and you just sort of expand outwards. So I've just started reading the book, actually. I'm only on the 2nd chapter, but if your readers are interested, like I said, it's called Colonizing the Galaxy in 8 Easy Steps by Marshall Savage, and he goes into a lot of technical detail on the engineering challenges.
And the first step is floating a city or cities on the ocean surfaces of the Earth?
That was his step 1, to create these self-contained, self-sufficient colonies that were essentially floating cities on the oceans,
And as the climate is warming, and there are some atmospheric physicists who are saying that we probably could be at the tipping point where it is not going to be a new normal that stays, that we are at a period now where there will be more and more energy and violence in the weather and atmospheric events, and that cities floating on an ocean might be more vulnerable or as vulnerable. I mean, what is your perspective right now on the Earth going for the rest of this century, where it could be becoming warmer and warmer and more ferocious fires, more floods, more everything, because the energy in the weather system is swinging like a pendulum?
Yeah, it's a great question. I certainly couldn't speak with authority on the matter. We know climate change is happening. There's a lot of people who don't think that it's man-made, that we're responsible, or that the contributions of the greenhouse gases and the carbon that we're releasing are negligible compared to natural changes in the Earth's weather patterns. But I think this all speaks to this idea of and I can't see the entire planet that just being under catastrophic circumstances. But I'm sure that there will be some areas that are currently feasible for human populations that may become infeasible in the future if there's flooding or change in sea levels. But we're sort of getting off a topic that I can speak with any expertise or authority on.
Yeah, I was going to bring it back that I only thought about that in terms of floating cities as his number 1 step. What gets us to the moon and beyond in his 8 steps?
Like I said, I'm just on chapter 2 now, so we'll have to do another interview next year.
Well, what are your steps? What do you think realistically will be the steps of transferring into an interstellar, interstellar Earth?
Yeah, let's go back a step and say what are some of the incentives before, so we can say, so before we say what are the steps required, let's say what would incentivize us to do that, because I think incentive is very important. What is actually going to cause us to put the time, energy, and effort in? And I think history has shown us that if we, as a people, focus our profound effort on one thing, we can generate incredible shifts in the course of civilization, be it the gargantuan manpower and resources that we've historically devoted to armed conflict between states or societies that have been world-shaping, like the American Civil War, the Taiping Rebellion in China, the conquest of the Aztec Empire by the Spanish, or the two last world wars. This focus of money and energy and resources and effort create these great shifts in civilization. And of course, that's an example of wars, but they can be cultural or scientific. So the great pyramids, the great cathedrals of medieval Europe, who incidentally, the construction of them took centuries. And so, we have shown a propensity for doing projects that may take tens or hundreds of years to come into completion. Another example is the Manhattan Project, where in a very short period of time, we created an atomic bomb, the Apollo program. But there had to be some kind of an incentive. So what would incentivize us to really go interstellar? And I think that there are a number of things that would give us that incentive to actually put more resources into becoming a civilization that explores interstellar space. Scientific discoveries are a very important motivator. So, for example, we spoke earlier of exoplanets. I think if we discovered a habitable Earth-like planet within 10 light years of Earth, and we had telescopes powerful enough to take a picture, can you imagine the effect that would have on the global population if they saw this blue-green orb, this Earth 2.0 that was within 10 light years of us? I think that would be an incredibly compelling value proposition.
And isn't the Webb telescope, if it gets launched in 2019, it is, I've been told, that it will be so magnitude beyond telescopes we've had in space before that it would be able to see the surface of Alpha Proxima, the planet, one of the planets in the Alpha Centauri system?
Oh, wow. I hadn't heard it was going to be that powerful. I mean, my understanding was that right now we don't actually optically image exoplanets. We infer their existence by certain secondary effects. So, for example, the Kepler Space Telescope observes this periodic dimming of stars as the planet passes in front of the star. There's this periodic dimming. And we can only do that with a fraction of stars that have the planets at just the right orbital inclination in respect to where we are on Earth, our location in the galaxy. But I was under the impression that they would be able to, for the first time, be able to make out that pinprick of light that was reflective of an exoplanet. But I mean, I would be surprised if it looked anything more than the moons of Jupiter using a 2.5-inch telescope here on Earth. You can make out the disk of Jupiter and you can see that there are these dots surrounding it. And I would imagine that the exoplanets would be able to be resolved like a small dot. But I'd have to do a little research after this call just to verify that's correct.
Yeah, I know it's supposed to be a huge exponential leap in the and one of the ironies we now have, I believe, isn't the number of exoplanets that have been reported or on a list, that they are over 1,000. It may be that it's over 2,000 or 3,000 now, and that there is yet, we have not found a single exoplanet that would be like Earth with large oceans and be at the right Goldilocks distance.
You hit the nail on the head, though. There are over 1,000 exoplanet discoveries. Last time I checked, which was quite recently, there are about 20 or so Earth-like candidates, in the sense that they would be roughly the right mass, similar mass to Earth, rocky content, the right distance. So I believe there are candidates, but perhaps the James Webb Telescope will reveal more information on this. But getting back to that question of incentive, we talked about finding exoplanets, but another incentive would be the discovery of indisputable evidence of organic life on a planet close to Earth in another solar system, or indisputable.
we prove that? What is the way we would prove that right now?
I'm not an expert on this, but just sort of speaking off the top of my head, I believe that there are certain gases that can be that you can
like
that only. Yeah, that are only renewed over time when there are life forms on the planet, and that we have techniques that we can spectrometry techniques, so we can figure out the content, the gaseous content of the atmospheres. But we'd be moving outside of my expertise as a theoretical physicist. But something else, though, we've had the SETI program going for some time now, the search for extraterrestrial intelligence. So if they had a successful discovery of an indisputable signal from an extraterrestrial civilization, then I think that would be an incentive for us to put great effort into interstellar flight. And you had mentioned it. We both mentioned this a couple of times. An existential threat. Right. If there was a known existential threat, then that would be potentially an incentive. But then we talked about. You had mentioned, what do I see as the steps required to make that a possibility? And I think there's really three things. What's the bridge to becoming an interstellar civilization? To me, it's step one, we need cheap access to space. Step two, commercialization of space. And step three, the expansion, the eventual expansion into space. So space is difficult to get to. It costs tens of millions of dollars for launches. I mean, going to the moon, it cost 150 billion. There was all the R&D costs, but getting to space is expensive. And so, Elon Musk we talked about him earlier, and he's working on a very heavy rocket. Right. And he's calculating $50 per pound with 150 tons to orbit for each launch. And that would be a cost per ton to Mars of just $140,000. So that's that's the price of a small house, of a house here. And so you could get a ton to Mars for that cost. And he envisions this vibrant ship construction industry producing dozens of these interplanetary transport, perhaps even hundreds or thousands per year. So that could potentially be disruptive.
And Dr. Obousy, isn't part of his thinking that Mars may have minerals, metals, and various things that we might not have in luxury on the Earth, and that Mars could become a production center if he could crack the whole issue of getting terraforming that would warm it up and all of that? I mean, isn't that part of their thinking, that Mars could be a brand new mass production center because it has new minerals and metals?
It's funny you should say that, because my three steps. The step two was the commercialization of space after we've got cheap access. So you hit the nail on the head again. And I couldn't speak to the mineral content of Mars. Again, it's not something I'm an expert on. But John S. Lewis was someone who wrote a book called Mining the Sky, and I think his background was geophysics. He was at one of the bigger universities. So Mining the Sky was his book, and he looked at the mineral content of the asteroids in the solar system, and he estimated that one of the closest asteroids to Earth had an estimated mineral content, metals that we mine here on Earth, of $20 trillion. So that's more than the GDP of the United States. And that's just one average, and there are tens of thousands of these. And so it's been said that the Earth's first trillionaire will become rich through mining asteroids, mining materials outside in the solar system.
Well, have you ever talked with Elon Musk about his theoretical idea that to rapidly change the climate on Mars and make it warmer, that he could set off a nuclear, I think an atmospheric nuclear explosion in the north or the south, and that it would rapidly transform the Martian atmosphere?
Well, I was thrilled to meet Miguel Alcubierre, but I've never sat down and had a cup of coffee with Elon Musk. I think that would be an incredible opportunity. It's been a while since I looked at terraforming. My understanding is that it's a process that would happen over many, many centuries. I don't know the exact steps involved, but I think certainly we need to be thinking outside the box, thinking aggressively of how can we do this. And like I said, cheap access to space was one of them. And if it doesn't happen through rockets, because rockets is just one paradigm, I met several times a chap called Dr. John Hunter, went out to see something he'd been working on. It's called the hydrogen gas gun. And so his idea, you couldn't launch humans, but you could launch payloads into space using essentially a very, very long, several 100-foot long gun that was powered by hydrogen gas. And he had this whole business model, and he had tested this gun and reached almost orbital velocities. And so that could be a paradigm shift if it comes to getting into space. Or, of course, some of your readers may have heard of the concept of the space elevator. And the idea there is... moving one model is you would shift a very small asteroid into geosynchronous Earth orbit, about 36,000 kilometers above the surface of the Earth, and that you would slowly, through some engineering process, start creating these carbon nanotubes and creating this thread that lowers down from this asteroid to the surface of the Earth. And the idea here is once you've got this physical link, be it through a thread or a column or whatever the material may be, that you can use electrical energy, like a conveyor belt, essentially. You can use electrical energy to get into Earth orbit, and that is phenomenally more cheaper. We'd be talking a few tens of dollars per pound to get into space, essentially. So I think that's one of the bridges. Those are the bridges to becoming an interstellar civilization. So cheap access, and then commercialization. Why would we want to commercialize? Let me ask
you a question before we move on. Would the space elevator then be used to replace something like a launch to the ISS, that you would use the space elevator to put satellites up, or what would be the end goal of the space elevator?
I would imagine that the end goal would be a complete replacement of rocket launch technology to be superseded with space elevator technology, just because of the huge differences in cost. Whether that would be immediate or whether that would be incremental, I couldn't say. Perhaps with one space elevator, you may be limited to a certain amount of tonnage per year, and so demand may outstrip the supply. So you may still have rockets launching things into space. But I would imagine that the grand scheme, the overarching goal, would be to have one or maybe more of these space elevators servicing all our Earth to space needs and requirements.
Wow. And have you ever talked with Robert Bigelow of Bigelow Aerospace about his blow up? I started to say buildings, but they are spaces. And originally they were going to go into the Lagrange points where they would stay the energy between the moon and the Earth. They wouldn't be going either way at a Lagrange point. And now I understand that he has a contract with NASA to use these blow up rooms or buildings on Mars, as well as at the Lagrange point between the Earth and the moon, and maybe on the moon.
I love those ideas. When I first heard the inflatable space stations, you kind of chuckle, but then you look a little bit more deeply into it and you think, wow, that's genius. We have these materials that can be compressed into very small volumes. They're very lightweight. And then when you get them into space, you can inflate them. And then you have these pressurized living units. So I haven't explored the design, but I am aware of them. I think it's this exact outside of the box thinking. That one day we're going to hit the jackpot. Space elevators, warp drives, hydrogen gas guns, terraforming. We need this courageous, pioneering thought process if we're going to become a spacefaring civilization. If we're going to colonize the planets of our own solar system and eventually colonize the stars.
And what is warp drive?
Yeah, so warp drive is a name taken from science fiction, really, straight from Star Trek. So the idea of in science fiction is the idea of a warp drive is that it's this engine that can make a spacecraft travel faster than the speed of light. And then, of course, that appeared in Alcubierre's paper. He used the phrase warp drive. I think he referred to Enterprise, Star Trek. And the basic idea is when you talk about a warp drive these days, it's commonly accepted that you're talking about some kind of an engine that modifies the fabric of space and time and allows you to travel at FTL speeds, faster than light speeds. And I'd be more than happy to give you an explanation, of the time we have left of the warp drive paradigm that I came up with at graduate school.
Yeah.
So I was definitely inspired by Alcubierre. I discovered his work when I was in my final year of university, and I started asking myself I was motivated actually by a paper by Kip Thorne et al. On wormholes, and they came from the perspective of what constraints do the laws of physics place on the abilities of an arbitrarily advanced civilization? So I'll say that again. What constraints do the laws of physics place on the abilities of an arbitrarily advanced civilization? And, what this allows us to do is, we don't have to worry at this point we don't have to worry at all about the engineering. How are we going to build it? How much is it going to cost? We're just coming at it from a purely theoretical perspective. What limitations does physics place on us? And, before we go into the main meat of my own model, we need some background. So some of the background ideas that I think we should introduce to your listeners, the following. That is, one, that space-time itself is not limited by the speed of light. So what I mean by that is we know from Einstein's special theory of relativity that nothing can travel faster than the speed of light, but the fabric of space itself is not hindered by this limitation. And then
it can be changed, folded. That Alcubierre, if that were working, we would be shrinking space, and then the speed of light would still be the constant rule, but we would exceed the speed of light because we would be shrinking, changing the fabric of time space.
Precisely, yeah. That rate of shrinking or expanding has no inherent limitations. So that's one of the first concepts we need to be familiar with. The next concept is that the universe is currently expanding at an accelerated rate. So we spoke of this briefly, this idea of dark energy. The next concept that we need to understand, and I'll talk about each one of these in a little bit more detail in a moment, but that extra dimensions may exist. In fact, that we believe that they may play a role in the creation of what we call grand unified theories. And so that's some of the fundamental ingredients. So we've already covered the idea that at the early epoch of the universe, at the time that the universe came into existence, there was this epoch called inflation, where space-time accelerated or grew faster than the speed of light. And so we think this is due to this ubiquitous exotic energy field called dark energy, which is exotic. It's a negative energy it's all pervasive. It's everywhere throughout the universe. And so the next question is, well, can dark energy ever be harnessed? I mean, it's very much a science fiction-y sounding question, but if we're going to explore what constraints the laws of physics place on a arbitrarily advanced civilization, then we have to ask the question, could we ever harness dark energy? So what might dark energy be? That's what we fundamentally need to ask. And my own work suggested that dark energy may be a residual Casimir-like vacuum energy that exists in the extra dimensions. So let's talk about why we need extra dimensions anyway. So we have four forces of physics that we spoke of earlier: gravity, electromagnetism, the strong and weak nuclear force, and they all exist using different models of physics and mathematics. So Einstein's theory of gravity relies on the idea that space-time is curved, and he uses the tensor mechanics and the mathematical language of relativity is very different to the language that describes the electromagnetic field, for example, which is based on the idea of these particles, essentially photons, and a different set of equations. So let's just come from the perspective of Einstein's equations and Maxwell's equations. So Einstein's describing gravity, Maxwell's describing electromagnetics, two completely different models. Now, in 1919, the physicist Theodore Kaluza attempted to unify these two theories. And what he did was he added an extra dimension, a fifth dimension, to Einstein's field equations. One of the fundamental features of Einstein, you have these 4x4 matrices, these 4x4 metric tensors, and they represent time and then the 3 dimensions of space. So they're a 4-dimensional matrix. But what Kaluza did was added a 5th dimension, and so you had these 5x5 matrices, and he put this special field in the 5th dimension. But what he found was that when you added an extra dimension to Einstein's equations, you could not only predict gravity, but also you could duplicate Maxwell's equations. So extra dimensions have been cropping up in physics since 1919. The most recent manifestation is in something called superstring theory, which is an attempt to unify all the known laws of physics. And so the most advanced expression of string theory is M theory by Ed Witten, and that has that's a unification model that's built in 11 dimensions, so 10 dimensions of space, and 1 dimension of time. So we spoke of the Casimir effect earlier, and I spoke of these waves, if you like, of energy that exist between 2 Casimir plates. Well, if you have a 5th dimension, imagine this 5th dimension that's small. It's very, very small and wrapped up. It's compact and it's circular. It's tubular. That same Casimir energy can exist around the perimeter of that circle. And so the idea that I explored was, what was the energy spectrum look like for this Casimir energy in the extra dimension? And what I discovered was that it had this very specific spectrum, this very specific feature, because one of the big questions in physics is, if you do have a small compact extra dimension, what keeps it small? Because we know our 3 large dimensions were getting bigger. We talked about that earlier. The universe is expanding. That means the dimension is getting bigger. The X, Y, Z, up, down, left, right, forwards, back, the universe is getting bigger. That's because space-time is expanding. So what is in these models of extra dimensions, the 5th dimension has to stay compact and stable. And so what I explored was the energy spectrum of the Casimir energy in this 5th dimension, and I discovered that it had a very specific signature that had something that we call in mathematics called a stable minimum. So just imagine, if you like, a ball. Imagine a hill, and it goes down, and then it comes back up again, it goes down, and imagine rolling a ball down. Well, a stable minimum is this point where this ball rolls down, but then it doesn't have enough energy to get out of the hill again with the rise on the other side, and that's what we call a stable minimum. And I found that the Casimir spectrum had this very specific stable minimum, which was reflective of a model that showed that you could have a compact extra dimension that stayed compact. And what was interesting was that the energy at this point, at this stable minimum point, the energy was non-zero. It was greater than 0. It was a negative non-zero energy, which I associated with dark energy. And so here's the fundamental point that I wanted to get across to you and your listeners. The idea was that dark energy is intimately related to the size of the compact extra dimension. So I'll say that again, because that's the key point. That dark energy is intimately related to the size, how big that circle is, the size of that extra dimension. So I took it one step further and said, what if you could technologically manipulate the size of an extra dimension? And if you could technologically interact with an extra dimension and change its size, you would be able to locally, around the vicinity of a spacecraft, modify the local dark energy density. And so that was the fundamental idea, that in the vicinity of a spacecraft, you would modify, you would contract the size of an extra dimension in front of the spacecraft, expand the size of the 5th dimension behind the spacecraft, and you'd create this exact, in mathematics we call it isomorphic. It just means it's the same as, you'd create this this effect that was isomorphic to the Alcubierre drive. But instead of it being based on general relativity, the idea was, this was based on the physics of extra dimensions. And so what I did, I did some calculations, and you can find all these publications online. You can search for my name, Obousy warp drive papers, and you'll find them online. And what I discovered, there are really 2 key numbers. First was the top speed that you could that was theoretically possible, but the important number was how much energy it would take. And my calculations would correspond to about 10 to the 28 kilograms worth of negative energy, and 10 to the 28 is around about the size of the planet Jupiter. So that was kind of my contribution to the field. It was coming from a different paradigm, a different approach of manipulating extra dimensions and discovering that you would need, less than the original Alcubierre paper, which suggested you need more mass energy in the universe. So that was really my main contribution, that we took the problem from being impossible to just being very, 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 very difficult.
And in my understanding and superstring theory is the fifth dimension has been compared to like Jello, in which the three that we are X, Y, Z, and then time, those four are embedded inside the Jello of the fifth dimension or brain, and then the sixth through the 11th are curled up somehow, as almost like one of the metaphors was, think of a theater and a stage, and that the theater sets have to be propped up, and that the other dimensions are propping up the fifth through the first?
What I did for my doctorate was that, so there are lots and lots of different models that you can look at. And so, to give you an example, when you first start to learn physics, you learn equations for, let's say you have a cannonball and it starts off fired upwards at an initial speed of 20 meters per second, at an angle of 30 degrees. And then you can use the laws of physics to calculate how far that cannonball, given the initial conditions, how far it would reach. But to make things simple, we just look at the problem in two dimensions. We look at up, down, forwards, backwards, or what we call the X and the Y axis. We don't bring the Z axis into play, because that makes the equations harder, and we don't get any more insight into the physics. Of course, if we have to do it, we'll do it. But when you're teaching physics and when you want to get a flavor for the physics, you kind of make it as easy as possible. And so what I did was I looked at string-inspired but Kaluza-Klein models. So this was where there was just one extra dimension of space, and its shape was like a circle. It was a compact extra dimension that was circular. And in fact, actually, in one of the later chapters, I looked at having two extra dimensions where the shape was toroidal, like a donut. But these were far simpler. I mean, it was still very, very difficult, but it's a lot simpler than when you go all the way up to the full M theoretic model. So in M theory, you have these 6-dimensional compactified spaces called Calabi-Yau manifolds, and the mathematics is incredibly in depth. My PhD supervisor, Dr. Gerald Cleaver, he did his PhD in string theory at Caltech, and he had expertise on these extra dimensions and their phenomenology. But my own model, I didn't go into the full M theoretic exploration. As a first pass, I just looked at having one extra spatial dimension that was a toroidal, circular to all intents and purposes.
And does any of this apply to the increasingly asked question, are we living in a simulated universe that is being projected by another dimension or from another dimension?
It's a great question. I'm not going to be able to speak with much authority on this, but I am familiar with the work, and for your listeners, the idea is essentially, let's say you've got a video game, and I remember playing video games when they first came out in the 80s, and the character in the game, it just does what it's programmed to do. But as the computers get more sophisticated, we now have virtual reality. I actually have an Oculus Rift headset in my place here. So it's a virtual reality headset. You get immersed in this other world. It's starting to, compared to what it was like in the 80s, where you just had these blocks of color that kind of looked like a person or kind of looked like a car, and then just 20, 30 years later, we have this virtual reality realm where it's starting to look really like real life. and we can look around, interact, immerse ourselves, and then slowly, we have these AI algorithms, and the characters in the game become more and more sophisticated. They're able to predict what their opponent's going to do more. And so the idea is, you just keep taking that to its logical conclusion. Could you ever reach a point where this simulation is so sophisticated that the characters all actually think they're real, that the entire universe, in a sense, is simulated within a computer program? And I think that's what you were sort of talking about here. This idea that this entire universe may be nothing more than an incredibly sophisticated simulation. And I know there are people out there, very reputable universities, who are taking quite seriously this notion and exploring the possibility. It's not an area I'm an expert on, but it's absolutely fascinating to think about.
Right, it really is. And the bottom line tonight, I think, is that we have heard in a variety of different conferences and television and news magazines about things like the Alcubierre drive concept and dark energy and why is the universe expanding. But the biggest question is, are we really going in the 21st century to become an interstellar family from Earth moving out into the stars? Do you think that there will be any interstellar travel between 2018 and 2100?
Well, you spoke, I do, and you spoke earlier of Starshot. Yeah, you spoke earlier of Starshot, which is the first serious effort to launch an actual interstellar mission. And just in summary for your listeners, Starshot aims to demonstrate a proof of concept for these ultra-fast, what we call nanocraft, these very, very, very small spacecraft, which would lay the foundations for a first launch to Alpha Centauri within a generation.
Yeah, so would that happen in the next 10 years? Because when I talked with Avi Loeb at Harvard, he said, we think we're going to do a demonstration within like a decade.
Yeah, from my understanding of the progress is that, yes, there's going to be a demonstrator within a decade, and then the final mission could be launched as soon as 2036. So that is well within a generation. I mean, that's just another 18 years away. So the idea, like you said, it received $100 million in funding from Yuri Milner. The final mission is estimated to cost around $10 billion. And so here are the key points for your listener. There would be actually 1,000 of these tiny spacecraft, a few square centimeters across, weighing just a few grams. And they would be launched by conventional means to high-altitude Earth orbit, and then ground-based lasers would fire at them, and they would accelerate them one by one at 100 kilometers per second. So that's 1,000 times Earth gravity. And they would reach their target's top speed of 20% the speed of light in just 10 minutes. And so, and because you have this swarm, they're traveling so fast, if they did interact with dust in the interstellar medium, they'd be destroyed or damaged. So the idea is, if you have thousands of these tiny spacecraft, a swarm, then that would compensate for the losses caused by collisions with dust en route. But there are a lot of technical challenges. I mean, everything has to be miniaturized. The camera, the computer, communications laser, and even the plutonium power source need to be miniaturized, and they all need to be engineered to endure this 1,000 G acceleration, and they need to survive collisions in space. And so there's all these problems, but it's exciting as well.
Obousy, we are at the end of the show, but we are leaving on this one solid timeline note that between 2018 and 2028, we could have the first demonstration of Starshot that was moving toward launching small wafer craft at least to 20% the speed of light, and that as the century unfolds, we will be trying to get to the speed of light. And I want to thank you so much for being on this program and talking about these subjects that have been words in on paper and in digital, but this is an exciting time to contemplate that we're moving into an interstellar generation. Thank you, Dr. Obousy.
It was an absolute pleasure, Linda. Thank you very much for having me on your show.
Well, that'll do it for another one in the can. Next week on Phenomenon Radio, Grant Cameron will join the show with us once again. For John Burroughs, Linda Moulton Howe, our very honored and special guest, Dr. Richard Obousy. Thank you all for listening. Stay tuned. Don't go anywhere. Jimmy Church has 3 more hours of live programming with Fade to Black. Tonight's Fader Night, right here on KGRA Radio. Have a great night and a great weekend, everybody.